Mendoza, and I am an engineering student at West Virginia University.
I'm Jackson. I'm an anthropology and GIS student at University of South Florida.
My name is Braden. I'm an engineering student at West Virginia University.
Hi, my name is Alan. I'm a civil engineering student at Chico State University.
I'm Casey. I also study civil engineering at Chico State.
And I'm Facundo. I study anthropology at USC.
Okay. So we are the researchers performing research at the Institute. However, this is a multi-year-long project that is being conducted by our principal investigators at USF, Dr. Nancy Mendoza and Dr. David Himmelgren, at WVU, Dr. Kevin Horner, and then at California State Chico, Dr. Pablo Pineda. And of course, our coordinator for the project has been Lisa Moreno at MBI. So a quick disclaimer before we start getting into our results. This is funded by the National Science Foundation. However, the findings, recommendations, and conclusions that we will present are not representative of National Science Foundation. It is representative of the authors. So this project is going to be presented in 6 major steps. First, we're going to talk about the problems that are occurring in Monteverde and the objectives that we want to solve. Then we're going to talk about how we address these issues with the methods and materials, and then we're going to run through the engineering results that we got and the anthropology results. Finally, this is used to kind of create a large evaluation of the sustainability of biohydrogenesis, followed by conclusions and recommendations for the region. So to start, the biggest issue in Monteverde that we are studying in this project is the release of untreated gray water. So gray water is about 75% of domestically produced wastewater, and it is made mainly from kitchens, sinks, laundry, showers, any wastewater that doesn't come in contact with toilet water. So it can contain a variety of different pollutants, such as soaps, chemicals, fats, oils, greases, any food particles, pathogens, microplastics, and then any other emerging contaminants based on the site. So for example, farms and hospitals are probably going to have very different types of gray water in their houses. So this can have, the release of gray water into the environment can have a variety of different health impacts. So first of all, as I mentioned, they can contain pathogens. So if you come in contact with it, or an animal comes in contact with it, they can get sick. In addition, if it cools, and you can sort of see it cooling in this picture on the right, this is a place where insects can breed, and some insects can also spread more diseases. So it's a cycle. Then finally, this can majorly impact waterways when it is put into the environment. So this can be done in a variety of different ways. It can affect waterways biologically, chemically, thermally, and it changes parameters such as pH, temperature, the amount of oxygen in the water, and the level of nutrients. So nutrients are one of the main focuses during this project, such as nitrogen and phosphorus. They are fine in normal levels. In fact, a lot of organisms need them, but when they are elevated, they become a problem environmentally. Eutrophication is probably the biggest result of nutrient pollution. So this is when there's an excess of nutrients such as nitrogen and phosphorus, as I mentioned, in a waterway. This causes an algae bloom where a lot of algae grow because they are no longer limited by the nutrients. After this algae bloom, when they die off and start to decompose, this removes a lot of oxygen from the water, which results in dead zones. So fish, plants, other organisms, they can't really survive without this oxygen. And so the green that you see in this is a aerial view of a gulf. All the green that you see is a large algae bloom. Okay, so one method to treat this this released gray water is biohydrogenesis. So this is a type of decentralized treatment system. Decentralized is meaning that it can be treated at the site that it is getting released at. It doesn't have to be sent to a wastewater treatment plant far away. So biohydrogenesis, they're basically mimicked after how a natural wetland would treat water in nature. They're going to be below ground for the most part, where water is going to be just sent through a bunch of gravel or other type of rock or substrate. And plants above it are going to be doing what's called bioremediating. So they're going to be taking nutrients, contaminants, metals, anything that you want out of the water, they're going to be responsible for removing a lot of it. It can be the water that is released, which is also called the effluent, It can be used to water plants, water your garden. It can even be used in the household to flush toilets, for example. So this can not only treat water, but it addresses some issues of water scarcity. So we can reuse water, and for some effluents that have high levels of nutrients, it can even be used as a fertilizer. Okay. So this shows basically the three main parts of a biohydrogenera that you should be familiar with for this presentation. So the picture on the very far right, this is where the water is coming in. This is the tank that is held in. It's known as the influent tank, and it also frequently has some sort of trap or mechanism to stop solid matter, grease, fat from getting into the system. After that, water is flowed through piping to get to the garden part. The plants are on top, and below is where you would have the substrate, such as gravel or different types of rock. That's where it gets treated, and then eventually it leaves through another pipe to the effluent tank. And after that, it can be released in a drain field or wherever it's needed to release it. Okay. So, as we sort of mentioned, there are several main issues related to gray water management in Monteverde. It lacks a centralized treatment system because it is a rural area, more rural area with a lot of differences in terrain. It's very mountainous. So it's difficult to have one centralized system. In addition, it's a more remote area with fewer population. So there's an improper method of gray water discharge, which is causing surface water pollution. As a result, there's a need for a sustainable solution to this problem. Now, it should be mentioned as well that there is a very high tourist population in Monteverde, typically around 200,000 people a year visiting, which just puts further stress on the wastewater infrastructure here. So to address these concerns that I just mentioned, we have three main objectives during this project. The first is to assess how well are biohydrogeneras working in removing contaminants out of the gray water. Two is the more anthropological approach, where we're going to be seeing what are community opinions on biohydrogeneras, how much do people know about it, and this kind of grounds us in general community opinion. Finally, we're going to be combining all of this to see how sustainable are biohydrogeneras for long-term in a region like this. Are they a good method of wastewater treatment?
Okay. So, as we mentioned, this is an interdisciplinary research project, meaning that we have engineers and also anthropologists that are teaming up on this. First, we're going to be looking at the engineering overview. So, over the course of the last 5 weeks, we have sampled 6 separate sites for the influent, or the water that goes into the system, and the effluent, or the water that leaves the system. We tested for pH, we tested for temperature, deoxygenated DO, we tested for electroconductivity, we tested for COD, nitrogen, and phosphorus. We also tested for greenhouse gases using a biogas analyzer, and we did the testing ourselves here at the Monteverde Institute, and then we also sent out samples to UCR. For the anthropology side, we conducted 28 semi-structured interviews, both with locals or people that live in the area that don't necessarily have a biogarden or even really have to know much about biogardens, and experts or people that are actively working in the field of gray water management. We also used pre-listing and tile sorting methods, as well as observations on site. We got 16 total local interviews and 12 expert interviews. We interviewed anybody that would be like a homeowner, business, or institution context. We also were developing a tool, the ESTA tool, or the environmental, socio-technical, and economic tool. Based on expert interviews.
Moving on to the sustainability side of our project, sustainability specifically was a very important part to include in our project because it includes future generations. If a project is not sustainable, it just poses a new problem during the disposal of a project for future generations and does not create a long-term solution. It also protects the environment as well as social and economic development in the future. We also, in conducting sustainability, we further analyzed it using our SDA tool, which is a multi-decision criteria analysis tool, also known as MCDA. And we were able to visualize the community impact in a sustainable manner. Moving on, we have our 12 sustainability metrics, which is also the focus of the majority of our study. Each metric is split into the 4 main categories of economic, social, technical, and environmental. The economic category consists of capital costs, which is the initial costs in creating and building the biohadanera, operation maintenance costs, which involves all of the costs for maintaining and keeping the biohadanera active, and of course affordability, which is over the entire 20-year lifespan of a biohadanera, if it is affordable for a single income household. Moving on to social, we have our maintenance category, which is how the society believes the maintenance requirements are needed for a biohadanera. The system intrusiveness, which is such as things that would cause an intrusive idea to the community, such as odor or maybe visual effects. And of course, community engagement. Does the biohadanera incite community participation? Moving on to technical, we have resilience, and of course, if it handles influxes in weather, high rain patterns, as well as the influxes in tourism. Implementability, such as if a biohadanera is accountable for space and can be implemented in our current situation. And appropriateness of technology, does the community have the active education and knowledge to build and maintain these biohadeneras? And lastly, environmental, which is our carbon footprint, which involves all the greenhouse gases in construction and maintenance of said biohadeneras. The eutrophication potential, as said earlier, with excess nutrients going out from the biohadanera, does it cause impact to different water bodies and therefore the environment? And then lastly, nutrient recovery potential. Can the water coming out of the biohadeneras therefore be used as irrigation to better help crops?
Thank you. Here we have an overview of our 6 sites. These were chosen and given to us by our primary investigators, all of which of these have been functioning in Monteverde for a year or longer. We have a wide selection of different sample sites. We have 2 homes, a restaurant, a brewery, a primary school, a hotel, and an institute. And so all of these deal with different amounts of gray water. For example, our brewery is dealing with the excess manufacturing of hops from the cerveceria, as well as their gray water from the kitchen.
So as mentioned earlier, we measure different parameters. Total nitrogen, total phosphorus, chemical oxygen demand, among others that we're going to be presenting on the next slides. So we collected this data by using 2 devices. One was the multi-probe, which is this one right here. That has those 3 probes. So we have the probe for the pH, dissolved oxygen, and electroconductivity. That all of them also measure temperature. Here is how we use it. So this is the influent tank for one of the biogardens. So basically, we use the probes and put it like in the middle of the tank so we could get an accurate measurement for those 3 parameters. And on this next picture, we're using this one, which is the biogas analyzer. For this one, we detected the levels of methane and carbon dioxide being released from influent and effluent tanks, as you can see on this one right here. And we also collected water samples from influent and effluent. So these water samples were later on tested here in the Institute lab for total nitrogen, chemical oxygen demand, and total phosphorus with test kits. And part of those samples were also sent to the University of Costa Rica for ion chromatography testing, which tests for ammonia, nitrates, and phosphorus, and biological testing, which is the test for pathogens, which is like E. coli or Helmindex. So as you can see in this graph, this is the average pH graph for all the sites that we tested on. As you can see, the ranges for discharge of pH in effluent, for Costa Rica, it's from 5 to 9, which all the effluents for all the biogardens, which are the red ones, are in that range. This shows that the biogardens are working in some way because they're neutralizing the levels of pH, as you can see in these graphs right here. Like site before, which is the restaurant slash brewery, you can see that it neutralized the level pH from the blue, the influent, to red, the effluent. Looking close at each site, we can see that for site B1 and B4, which is B1 is the institute and B4, as mentioned, is the restaurant. It's really close to the bottom limit of 5, so it should be monitored a little bit more constantly.
Thank you, Alan. Let's see if I can. And our next parameter here is dissolved oxygen. Dissolved oxygen is the amount of oxygen content that's available in the water. Things like fish, microbes need this oxygen in order to function and survive. In our case with Biohardinaris, oxygen is often used by the microbes to break down the biological and non-biological components that we put in through the influent water. We can see that DO decreases in 5 of the 6 sites. That means this oxygen is getting used up by the microbes and non-biologic processes in the Biohardinaris. And there, we can see here B2, which was the hotel, had a very high starting influent DO, and it decreased a lot, which means there was probably a lot of activity going on in that Biohardinera. However, these are all below the wanted threshold in Costa Rica of 5 milligrams per liter, and some things that could be done to improve that, which would make effluent streams healthier, provide more oxygen for the organisms after the Biohardinera, would be to have these influent or effluent tanks more exposed to the air. This allows a more free change between the atmosphere as well as the water, or having it sort of a mini waterfall system, because as that waterfall splashes, it lets in more air and therefore aerates the water, putting more oxygen inside. Next, we have chemical oxygen demand, which is very closely tied to DO. Chemical oxygen demand is the oxygen needed for microbes to oxidize organic and inorganic material, as well as it oxidizing on its own. High COD means there are aerobic conditions, which means there's very little dissolved oxygen left in the water. And that's not what we want. We want to reduce the COD. And you can see on this graph here, as DO is reduced, meaning that oxygen is used up in the water, COD percent removal increases, which means there's less COD, which means that oxygen is being used to decrease that COD. And here we have our COD graph. We can see they all are unfortunately above the effluent standard, but it is our best performing metric. And we can see the biggest increases at site B1, which is the institute, and B4, which is the brewery. And next we have electroconductivity. This is the measurement of, this is the measurement of water's ability to conduct electricity. This is done through total dissolved solids and ions within the water. Something you can think of is that you may know salt water is more conductive than fresh water. This is because of the extra total dissolved solids and salt ions within the water. EC represents a kind of a crude way to also calculate total dissolved solids because they're that closely related. And we can see that it wasn't the best performing metric with a percent removal from -34 to 49%, which means some effluents had higher EC than the influent, which means things got added within the Biohardinera. And next, our first nutrient is total nitrogen. This is one of the first nutrients that contributes heavily to eutrophication, which Alyssa mentioned earlier in the presentation. 5 of the 6 nitrogen measurements for the Biohardineras were below the Costa Rican limit, which was 50 milligrams per liter. The only one that was above was the business/brewery, with the effluent just barely above, but also was one of the best performers, reducing its total nitrogen by a large margin. And total nitrogen is just the measurement of all nitrogen compounds measured within the water. And then high levels of total nitrogen in the effluent increases eutrophication potential by a lot. And our second nutrient, total phosphorus, similar to nitrogen, but the performance here was a little worse. It's the measurement of all phosphorus compounds in the water. We can see in this comparison graph between nitrogen and phosphorus, the blue nitrogen had a much better percent removal than the nitrogen, with sometimes phosphorus compounds also being added within the biohardinera. And we were also often getting ranges for phosphorus that were below our testing kit's capabilities, which means it contributed a 0% removal rate for that biohardinera. And then, of course, higher effluent rates of phosphorus also increase eutrophication potential, which can harm the environment post-biohardinera. And finally, for the aspects we've measured, it was biogas. Biogas, we measured CO2 and CH4 with our biogas analyzer, mentioned earlier by Alan. This is important because they are both greenhouse gases, with CH4, methane, being a more potent greenhouse gas than CO2. Our biogas analyzer unfortunately didn't work super well. We were able to get some CO2 readings, with the brewery measuring up to as high as 4.9% composition of the atmosphere. But yeah, we couldn't get very solid CH4 measurements. So we did a general calculation based on the flow rates for each biohardinera, as well as the retention time, meaning how long the water stayed within the system. And these are these calculations in kilograms per day of methane, CH4.
Okay, so to kind of give a little bit of an overview of the results we just presented, you can look at this colorful graph. So it's green is better performance, red is lower performance. Now these values that we chose are COD, total phosphorus, and total nitrogen are ones that are frequently measured in different studies of biohardineras. And the values that I used to kind of measure how well it's performing, I just compared it to the average values that we are seeing in other literature. So for a lot of sites, they're on the lower end of performance. Number 3, which is a school, is definitely one of the higher performing biohardineras that we tested in this study. A lot of them ranging in medium, in the medium area of removal for a lot of these parameters. We do see a lot of red. The houses and the hotel are not doing very well for any of these 3 parameters. And COD and total nitrogen are the better performing parameters. Again, with total phosphorus, we don't 100% know for some of the sites, because our test kits could not pick up the range of phosphorus that we were getting. So it's possible that the total phosphorus values are much better in terms of removal, but seeing that a lot of them are adding total phosphorus to the system in the effluent, we do not believe that it's likely that they're going to be much better than the values given.
All right. So to ground our research in the reality of the community, we applied some anthropological methods that includes interviewing experts and locals, specifically experts that do wastewater management, specifically gray water. We also deployed free listing and pile sorting methods. We then took all of the data that we collected from our interviews and our pile sorting, and we coded it to highlight similar themes or concerns from the community. The goal of our interviews was to gain critical perspective, context, and knowledge from locals and experts to properly assess if biohardineras are a practical system that the Costa Rica of the future can actually rely on. So, speaking specifically about our interviews, once again, we had 16 total local interviews. We had 12 expert interviews. If we were given consent, we also recorded and then transcribed the interviews. We normally had at least 2 students conduct an interview per participant. So here we have our instruments that we used, or the questions that we used on locals and experts. For locals, we normally ask things like property information, what they thought or their opinions on gray water management in Monteverde, what they knew about biojardineras, and any information if owners had them. We also asked them to rank the four ESTA categories when thinking about whether or not if they wanted to build or own a biohardinera. For the experts, we asked them the disadvantages and advantages of biohardineras. We also went more in depth on the ESTA tool and ranking and weights. We also asked them like social technical rankings, specifically in the context of homes, businesses, and then institutes. Some questions that you would see in the expert interview would be like assign a weight to each item of the category, capital costs, operation maintenance, and affordability to see what they thought was more important. For the locals, we would ask things like, if you had a biohardinera, what would you want to do with the water that it produced? So the key findings from the interviews, experts really put emphasis on the site design and maintenance, prolonging these systems and making sure it's actually designed properly for the place that it's actually treating was very important. Locals like to speak mainly about the affordability and ask mainly questions and curiosity around how they would be able to build it and how easy it is to actually implement the system, especially in more cramped areas. So it looks like there's kind of a lack of information or availability to gain this knowledge, space, and support. Decentralized water systems are not a one-size-fits-all. Different amounts of available soil space, slope, water use, any other factors can make site personalization really critical for this kind of success. Prolonged success of these systems, according to experts, really heavily relies on community engagement and maintenance. So for locals, we're going to go ahead and talk a little bit about the perception that we gained from the interviews with locals. It seemed that only 1 out of the 16 participants that we had interviewed had a biohardinera, but 10 were actually familiar with biohardineras, and 9 were actually willing to implement the system. The impact that we can see when we asked the question, how does gray water impact the environment? Nobody responded very positive. Nobody responded positive. 1 responded it's neutral. 8 responded very negatively, and 5 responded very negatively, which means that there is a understood perception that gray water does negatively impact the community. We also decided to ask, what do people know about biohardineras? Are we familiar with the system? Most people, as we saw, are familiar with the system. We concluded that this is because Monteverde is a very tight-knit community. Everybody shares information, and this kind of knowledge is free-flowing. We have quotes like, I'm very familiar with the idea. I've not worked with them, but I've seen them here at the Institute. I know how they work. I know what their objectives are. I know how they're constructed. I know how much they're typically played for, and I know that they're sometimes typically abandoned as well. When asked disadvantages and advantages, advantages are that it's very low tech. Doesn't require a lot of maintenance or knowledge to actually produce. We can also, another advantage was no requirement of energy. There's also a reduced gray water output through the treatment, and also easy maintenance, relatively speaking. Some of the disadvantages that people had pointed out, 4 participants in particular identified the need for space for a biohardinera as being a disadvantage, and then 4 participants couldn't actually find any disadvantages for biohardineras at all. Some of the quotes that we saw were they're pretty low in zero works. It takes space, and most houses are very tight, and there just isn't really that much space. Outside of interviews, we also use pile sorting and word cloud technique. A word cloud is a visual representation of data. We ask participants, please list all things people consider when deciding whether to have a biohardinera. A bunch of these little paper squares. We ask them to write down all the factors that they could think of, and then we ask them to separate it into 2 or more categories of their choosing, and then rank them. The bigger the word in the word cloud, the more importance that it has. This is what we gained from the data that we had collected. As we can see from the word cloud, aspects of the biohardinera that participants gravitated towards are more technical questions. Words like space, plant type are some of the most frequently recurring words among all participants, with economic factors generally being the lowest. Technical was mentioned, followed by environmental at 26%, social at 21%, and economic at 11%.
Go, sir. Thank you. So these next slides are going to be a frequency analysis of the responses that we got from our interview instrument. Frequency analysis is pretty much just a summary, a tally of each type of response that we've gotten. This first one here is a maintenance frequency analysis. The question that we prompted the experts with was the maintenance requirements of a biogarden are. It's notable here that the home maintenance is significantly lower than the other two options. Here we have the orange being home, the blue being business, and the green being an institute. Go to the next one. And so this is now our system intrusive analysis, again, for that frequency. We asked how many nuisances are associated with a biohardinera. An example of a nuisance would be like insects, odor, or just leakage. For the overall aspect of it, homes, again, are leaning towards the left here of less nuisances than the rest. Go to the next one. And so here we have the implementability of biogardens. This is, again, you can see an emphasis over here on the more implementable side than the less implementable. It's notable that the only person who voted that it was barely implementable is someone who has built 3 biogardens themselves and is pushing for more. They have seen a lot of different types and worked out with different designs. Go for the next. And so here we have our appropriateness of technology. This graph might be a little bit confusing here. This one is actually most appropriate. So again, overall, it is deemed appropriate across the board for both home businesses and institutions. A gap that is apparent between the experts and the locals that we've noticed is that experts believe that it is a lot easier of a technology, most likely because they're familiar with building them, and the locals are less familiar. Go for the next. So here's a satellite image from 2016 and one from 2025. It shows the growth of Santa Elena over the past 9 years. The disparity between locals and experts was really apparent with this one. Experts typically think that there is space. Some quotes of this, we have someone suggesting a bathtub-sized biogarden that everyone's capable of. But again, locals are saying that there's less space. Go for the next one. And so here's some more quotes with the experts that we have. Majority of experts believe that a future where biogardens are used in homes, businesses, and institutes is possible. The most notable thing here is that the maintenance and community are intertwined. For biogardens to be implemented successfully, you need to have a community of people who are willing to work on them and then hold themselves to it, consistently work on them. So what does all this mean? An analysis of this is that there's clearly some barriers for entry to get a biogarden. One of this would be cost, another one would be space, and then technical uncertainty. Education, again, is a major factor here. We can see apparently that there are huge motivators for the Monteverde community to implement these. We have a lot of emphasis on environmental issues and water reuse. Frequently through all of our interviews, both local and expert, we heard the word depends. This can be applied to like both the construction and the management of a biogarden. Every biogarden needs to be specific to every type of location and every type of wastewater that it's dealing with. Overall, the community is curious and interested in biogardens, but there are some exterior restrictions to implementing this. Here's Casey.
Finally, we're moving on to our sustainability analysis. Once again, sustainability is important for the longevity of a project to also ensure future generations can also use the biohadneta. And we are also looking at the 4 categories: economic, social, technical, and environmental. So what is an LCA, or a life cycle analysis. So a life cycle analysis examines all the stages of a biohaneira, including construction and materials, the use of the biohaneira, and then finally the disposal at the end of its 20-year lifespan. And an LCA is specifically what we use to be able to determine the total sustainability of biohaneiras. And it also helped us develop the S-Day analysis assessment tool that determines the total community impact. First, we will look at our economic results, looking first at capital cost. And we can see by this graph that the highest, of course, was the restaurant, which is the biggest system that also accounts for sewage. And therefore, we will treat it as an outlier. So the next best one, well, not necessarily best, next highest one is the institution, which, as you can see, is the highest flow. The flow rate goes from least to the left side, most to the right side, which also gives us the pattern of higher the flow, higher the system, the more the cost. We can also see that most of the cost for all of the systems, as seen in that red bar, is actually the constructed wetlands, which involves the rocks, the piping, everything that goes into the actual filtration part of the constructed wetlands, which could also be adjusted by using sustainably sourced materials and minimizing the cost actually required for the biohaneiras. Next, on to operation and maintenance. We can see once again the brewery has the highest maintenance cost, which it also accounts for additives required for treating such things as sewage. So once again, it is our outlier. And our key takeaway from this is actually that the houses, against most community belief, have the lowest maintenance cost, little to no cost associated to maintaining and keeping a biohaneira active. And lastly, on to affordability. Affordability is measured over the entire 20-year lifespan of a biohaneira and how affordable it can be to a single income household at minimum wage in Costa Rica. And as we can see, the yellow and green lines represent 3% and 10% of total income for the 20-year period. 3 to 10% is the approximation of affordability for a household based on sanitation and water uses, and therefore we can actually see that almost all of the biohaneiras, excluding the one for the brewery, which is our special case with sewage, are all within the affordability metric, either under that 3% of very affordable or within the 10% of basically affordable. And of course, the restaurant is above 25% of a single income household, but you wouldn't afford a restaurant under a single income household. Moving on to our social results. On this graph, it's a little different. The higher the bar, the greater the impact, the worse it behaves. And of course, once again, the restaurant has the highest social impact with the most system intrusiveness and the most maintenance. But across the entire board, you can see the yellow bar, which actually is community engagement, which implies there is little to no community engagement at all of our sites. And surprisingly, we see it's the highest in both the institutions, the school and the institution, which implies that even a school that incites community engagement in all other aspects is not doing it within its biohaneira. We also, this graph is solely based on expert opinions associated with each of the sites. And if there was a site that did not have an expert specifically from that site, it is based on all of the expert opinions values over the entire interview. Next, we move on to our technical results. The highest technical impact was this time the hotel, it was not the restaurant. So the higher the bar, once again, the worse the impact, the worse it behaves. So the hotel has the worst technical impact. It has smell issues and is not necessarily efficient for the placement of where it currently is, shown by how high the bar is. We also see that specifically implementability, which is that red bar, is a consistent issue across all the sites, meaning that the way where they're being put is not necessarily perfect for their situation, according to experts. And lastly, we see the restaurant actually has zero impact. According to this graph, there is no bar, which is opposite to all of our other graphs. This doesn't mean that there is no impact on the community. It just means that there is very little to no impact compared to the rest of the sites that we looked at. And therefore, it creates limitations for this analysis method because we cannot see the true impact of or true technical impact of this biohaneira. We know there is still some, but compared to the rest, there is not. And lastly, moving on to our environmental results, we look at carbon footprint, which is, of course, greenhouse gases. We see the majority of each of them is that yellow bar, which is methane emissions, which we said we calculated earlier. And of course, the restaurant has the highest methane emissions, it has the most area to emit methane as well as handle sewage, which of course is mainly methane. But then we see that the next highest carbon footprint is the hotel, with mainly infrastructure causing a problem, meaning that with the blue bar you see means most of those biojardineras were built with concrete, which incites a higher carbon footprint. But as you can see, the other ones are actually quite low, meaning you could build them without having a high carbon footprint. Now, eutrophication potential. As said earlier, it is the amount of nutrients put into water from the biojardineira. And the restaurant, once again, is high, but so is institution 1, meaning the more nutrients that go into the biojardineira, the more that comes out. So both of those have the higher flows on this right side, meaning that they are putting more out, which shows that there is a higher eutrophication potential and a higher impact on possible water bodies in the Monteverde community. But the rest actually have very little effect on aquatic life according to how much they are putting out into the environment. And lastly, nutrient recovery potential. Once again, the more nutrients that go in, the more that come out, showing in the brewery and institution 1. So according to about half the flow going in, coming back out, we can account for new nutrients being able to use that water for irrigation, shown by the higher bar. We can see nitrogen has, of course, a higher impact and less phosphorus coming out of the system. But the major repercussion is, yes, there's more nutrients coming out that we can reuse, but if it isn't reused, it is causing that eutrophication problem. And lastly, all of our data sent before this funnels into our sustainability analysis, or what I like to call our ESTE tool. And it shows our total community impact. So on the right here, these graphs are actually the same. The top one just shows all 12 of our metrics for each of the sites. This one is a very simpler graph that we can see across the board, the 4 different categories. So of course, once again, our restaurant is the outlier, having the environmental impact be the highest, but the next highest impact, once again, the higher the bar, the worse the impact on the community, is actually the hotel, having appropriate use of technology, or all of the technical metrics, as well as resource recovery potential being the highest impact on the community. And then of course, the lower the bar, the better the biojardineira behaves, and we see that in institution 1 over here on the right, which also gives way to economies of scale, which means that the bigger it is, the more efficient it can behave. And again, we see that with the highest flow, which we also see the lowest flow behaves the worst sustainably. But as Alyssa said earlier, it actually is the opposite way for water quality, giving way to possible maintenance and implementation issues.
All right, thank you, Casey. Moving on to our conclusions and to wrap things up. Go ahead and click next slide. So in conclusion, even though some of these biojardineras were not meeting effluent goals and were not performing as well as we had hoped, through our research, we still think that they're a viable option for decentralized gray water treatment. And we think that these gray water solutions in biojardineras can be effective if proper education exists, they're designed intentionally, they are maintained properly, and local support structures are available within the community. So firstly, if proper education exists, through this research, we have noticed that some inconsistencies out there, whether that's on the internet or within the community, and just streamlining some of that information and making it more consistent and accurate can help the situation a lot. And as well as that is intentionally designing. Biojardineras need to be specifically designed for the home, institute, or business they're implemented in. You can't put a huge size scale business rated biojardineira for a household, and you can't do the opposite for a business. And it's also important to keep them maintained properly. They are a biological system. At the end of the day, they need to be maintained properly. This is because it's a much lower cost option doing it the biological way than, let's say, a centralized treatment plant. And then local community support. This also involves education, but having a network of people that know about biojardineras can help and assist those who own them. Research also shows that environmental and economic impacts were the largest seen through the ESTE tool that Casey presented, as well as the ESTE framework enables a holistic, site-based sustainability assessment for these biojardineras. And moving on to our references, or sorry, recommendations. The first recommendation we have through our research is community education, as I mentioned before, educating the community. This could start, let's say, at the elementary school level, getting them introduced to it, and then continue education programs, maybe even at this institute for adults who would be interested in implementing these systems. And services, if there was a company that would be interested in doing this, much more people, as we saw through surveys, would be interested in implementing these biojardineras. That way they could get help maintaining, building, and learning about the biojardineras. It's not all on the way to their back at a household level. Next, as I mentioned before, is design, having tailored designs based on your location, what type of building you own, and future research. We have a couple future research recommendations based on our research. We would like to redo a affordability assessment if there was a company available to do these processes, because it would be vastly different prices. It might be more, it might be less. It could be less if it was streamlined, but we'd want to redo that. We'd want to have more sampling days to just get a wider data set, as well as less interviewees directly connected through the Monteverde Institute. This could have brought some bias into our research, as a lot of the interviewees we got were through connections here. And thank you for everyone for listening in. Thank you to the homestays. Thank you for everyone who participated in this research. And thank you to NSF for sponsoring this program. Thank you.
Now we would be open to any questions. If anybody has any, we would love to answer some.
Yes.
Thank you. This is very exciting to see the results. And I think a lot of them are really applicable for us to move forward with our work here and hopefully other organizations as well. So thank you, first of all. I'm curious, and if you said it and I missed it, I'm sorry. Did you take into account at all either the age of the system or age since renovation of the system? Because as I think you know, at the Institute, we had renovated our system, like taken all the rocks out, cleaned everything not too long ago. And along with that, if you are familiar with anything in the literature about kind of the time for these systems to mature, I guess, in the biological sense, to get to their optimal point of that biological processing.
Okay, so a couple points in there. So with the one specifically at the Institute, that was the only one that had an increase in dissolved oxygen, and I believe that is directly related to the rocks being recently cleaned. In biojardineras, there's typically a lot of buildup of algae or microbes in the substrate itself, which removes a lot of the dissolved oxygen, and I think that's why it had an increase, because it wasn't being the oxygen wasn't being removed as much from that specific system. It does, the lifespan of a biohardinera, how well it performs based on age kind of differs between different metrics. So for example, the longer it runs for, the plants will start to decrease in the amount of nutrients they can remove. And so you might have to replant them or just prune them. But the longer that a biohardinera exists in general, the more microbial activity will occur in it. So it can also become then better at removing nutrients and removing pathogens. So it's kind of something you have to, that's like where the maintenance aspect comes in. You have to keep up with each different aspect of the biohardinera for it to be functioning well at the point in its lifespan. Oh, we had someone behind us.
Did you notice any differences in efficiency between biojardineras that were densely planted and those that were like not so densely planted?
Yes. Do you want to take that one?
I'm trying to recall which ones are densely planted.
Both of the home systems we looked at, as well as the school, were very densely planted. However, there was also a very low flow rate for those. So it's hard to compare them to the other systems, but those ended up generally having better water quality. But we don't know if it's because of the higher retention time because just less flow, or if it was because of the plants. We can't really point to it.
Yeah, you want about 80% plant coverage is what literature suggests, and if it's planted too close together or too far apart, you can have issues with like dissolved oxygen not being properly removed or removing too much, for example, if there's too many plants. So that's like one of the reasons why each site is so specifically tailored, like where am I gonna put the plants in the system, how many plants, and that's like a great opportunity for a business or institute to help provide like that specific information at each site.
Was anybody using in these systems any kind of additives, like putting EM and?
Yes.
The only system that had additives, which was the restaurant and brewery, because they had to add antifungals as well as magnesium nitrate in order to also treat the sewage before it goes into the biohadneta, because their system is a little bit more special with those chemical additives treating something like sewage, but also so then it does not increase the amount of nutrients that build up in the biohadneta, because they also have a drain field and a septic tank, 2 septic tanks, I do believe. So their system is a lot more complicated with the addition of sewage, but that is the only one that actually has additives.
And in the capital cost, it's the blue bar for number 4. So you can see that that kind of composes like a pretty large portion of the capital cost.
And what do you think, based on the like literature searching that you've done about biological additives like EM? I know there were some folks in town recently who sell those products, and it's just something I don't know. I'm not familiar with the research on it. I don't know if you looked into that at all.
I think we didn't look into that as much, but I will say for sites where we're seeing nutrients increase in the effluent, I think that could be an interesting kind of avenue to look down, because we don't exactly know why some of the nutrients or dissolved material is increasing. So there might be a need for an additive to kind of control that somewhere in the system. But that's definitely something we would have to look into a little bit more.
In addition to that, we, due to our limitation of what we can test, such as total nitrogen, total phosphorus, as well as waiting for UCR results, we don't know exactly what those chemicals would do in the output if it stays throughout the entire system and then also affects the effluent going back out, which may affect if it could be reused for irrigation or if it would further implicate higher eutrophication levels. So due to the minimization of our study, we did not look into that, but possibly a further study analysis could be done on chemical additives or natural chemical additives.
Yes.
I know it's outside the scope of the study, but I'm sure you all thought about it. You're smart young folks. Did you have any thoughts on alternative technologies to biogardens that you thought might look attractive in this sort of environment?
In my opinion, not necessarily an alternative to a biogarden, but building them a different way. I do believe most of them are following a certain script that is one for all, and as Braden said earlier, they do not fit one for all, and there should be something there that can customize your biohadoneta for your space, for your water going in, for what you want to use it for, like irrigation for plants, and something else besides the one-fits-all instructions for a biohadonera.
Yeah.
We actually had a couple experts mention, like when we used the quote about a bathtub-sized system, someone even mentioned physically having a bathtub like above ground and kind of having the system go through that. So you can have like tanks, different types of above ground systems that kind of function the same, but aren't in the ground, so they don't necessarily take up that same amount of space. There's other types of wetlands where you might have them like above ground, and so the water itself is above ground, but that's not necessarily great for tropical environments because there's going to be a lot more insects and animals drawn to that area. So I kind of think that like the water physically being below like soil or rock or something is like a very good alternative for tropical areas like this.
Yeah, it's kind of it's either a situation that we either have like no system whatsoever and it just kind of goes out into the environment, or some sort of like centralized system. And I guess the point of the project is to see if like we can find something in the middle there. And there were a few experts, again, it's kind of outside of the scope of like our research, but there were a few experts that have mentioned things like permaculture these types of like, just trying to think outside of the box and think of like how we can find like that sort of happy middle where at least there could be some treatment to gray water, since the situation is that there's just most of the time no treatment whatsoever.
Facundo and I also had an interviewee. We talked a lot about, as an alternative technology, combining your gray water into your septic tank. Just the problem with that around here is that can often overload a septic tank, as people only want to pay for the minimum size they can get away with. So it can be hit or miss with that.
Thank you.
Sí.
Did you research anything on the legal aspect of rainwater? Because it feels now it's optional, it's not something you have to research.
So, could you go, so when you say legal, is that like, is someone allowed to have a biohardinera, or like the results that the water has to reach?
There's any laws that actually tell you in Costa Rica that you have to treat the rainwater?
From what we know, there is not. There's of course the limitations of nitrogen and phosphorus that we said earlier of what can be put out. But for the most part, gray water is not necessarily regulated.
And the levels are not necessarily enforced either. It's kind of just like these guidelines exist, but we're not, in all regions, they're not exactly going to be checked. So I think that would be a very interesting avenue of research as well, to see kind of how the government views it. Yeah. Mm-hmm.
I've got a couple of questions. A lot of it has to do with wanting more information from the background of all of this. And for those of us who have, or one of those, if you're going to give us a report on our system with recommendations, that would be really, really helpful. We talked about it some, but it would be really great to have it in writing.
Mm-hmm.
And the other is following up on the idea of having professional services around this. It seems like one of the natural places to start would be with the experts that you interviewed. And so it would be really great to have a list of those experts as a beginning to see who might be interested in helping to design, install, or maintain other people's biogardens.
That's fantastic. That would definitely be kind of a resource we would work on and could possibly compile later if the experts wanted to be on that list. I think that's a great idea, because we already have established some people that do have that knowledge. Yeah, that's fantastic.
Because we also do like we've noticed though that like whenever we mention things like education and whatnot, that it's not necessarily that people don't really like know about the system, because everybody needs a septic system, for example, and not everybody exactly knows like all of the technicalities of how their septic system works, right? You have a company that will come and then do it for you, and then somebody that comes and like maintains it. So if there was a similar infrastructure with that, with like biohardiness, maybe that could be like a decent way to like get this technology out there as well. Having somebody that can handle the technical aspects and people that are willing to just simply like pay to have the system and then have the company come in and maintain it, that could be like a decent avenue. And yeah, it was kind of mentioned at least through like some experts and even some locals that like that would be like an interesting avenue to go down. So I'm glad that you brought that up.
Thank you.
All right, thank you, everybody.
Yeah, thank you.
So much.
Yeah.
Muchas gracias a todos por participar. Recuerden que por ahí hay que tener y muchas gracias por participar con las actividades.
Muchas gracias.
Gracias. Luisa. Ahí.
Se apaga esto.